Good afternoon, everyone. Thank you for joining once again. It's nice to see some good attendance here. So today we have Dr. Naina Ralaivaosaona, and he is going to be talking about randomness and prime numbers and so forth. So just to give a bit of an introduction, he did his undergrad and honors in pure and applied mathematics in Madagascar, which I think is very cool. Yeah, it's just a cool fact. And he then studied at Ames in South Africa and went on to Cambridge, and where he did his maths tripos, and he did his PhD in Stellenbosch. And yeah, he's been a lecturer for a long time now, mainly in the field of analytic and probabilistic combinatorics and analytic number theory. So yes, without further ado, thank you very much for being here, and we look forward to your talk, Dr. Naina.
Thank you, Rocco. So I myself assumes I've managed to sort of avoid giving a talk for almost a year now, but I think this time I couldn't run away anymore. So here it is. So okay, so I'm going to start sharing my screen. I didn't prepare a slide. As you know, it's still busy time, so I'm just going to write on my computer. So let's switch off my camera. Okay, so yeah, I don't see you guys anymore because I see my screen. So if something goes wrong, you could just WhatsApp me. I don't know, Leslie or Gareth or whoever is in the audience. Just WhatsApp me if something goes wrong, or just speak. Okay, so I was okay. So let's just talk about prime numbers plus randomness and all that stuff. So of course we're talking about sequence of numbers 2, 3, 5, 7. What is next? 11, and so on. So you know that there are infinitely many of them, and the problem I think is when you study number theory. In fact, what's really happening is that if you study numbers, arithmetic, so if you study multiplicativity, then you can't run away from primes because they're sort of the building blocks of numbers. So, but then the problem is, how do we locate them? And that's the biggest problem, is location of these numbers. Where are they? So that's the problem in analytic number theory. So today, I'm not going to talk about rigorous mathematics. I'm just going to talk about lots of heuristic arguments that I think people should use to kind of understand theorems, why certain theorems or conjecture make sense, and that's what I'm trying to do today. So let me just start with the basic, not basic, but sort of the first question. So the simplest question is, how many primes are there less than a given number? And you have to consider this function. So pi of n, so n is a natural number. So this is then the number of prime. I'm going to write p for primes all the time, but let me write it. So p prime such that p is less or equal to n. So this is a function. All right, so this is a function, and then you want to know how many, how does this function behave? And it was a talk, I think, by Dylan at some point about the prime number theorem, so about this function. And what happens is that so as n tends to infinity, the prime counting function is roughly about, well, n over log n. The meaning of this symbol here is the following. So the limit as n tending to infinity, so very large n, of this function divided by n log n is 1. So that's the prime number theorem. So that gives us a bit of a understanding where these primes are. So prime So abbreviation would be PNT. Okay. So yes, let's see how. I'm just going to show you quickly. So I'm going to stop sharing this. I think I plotted something. Okay, let's try to share this. Yeah, so you guys see my browser?
Yes, we can see.
So you could actually just do this. I'm using Sage, so I'm generating all primes, and I'm defining the prime counting function, and I'm going to plot them. I'm going to plot the two functions, the actual prime counting function and the function n over log n, which is x over log x and this. So if I'm going to do that from 3 to, what is it, 5? Whoops, that might be too big. So, well, I mean, it's kind of close, but it's not really close. But it's, you know, it's there's a small distance, but it's clearly going into the same direction. So the blue one is the actual prime counting function, and the red is the approximation. If I take the quotient, then let's say if I divide them, it should tend to 1. And yeah, you see, it's early on, it's something like 1.1, and then it's kind of slowly getting down, and it's kind of stabilized. But it will eventually tend to 1, and that's what the prime number theorem says. So let me go back to my other screen. Okay, so the prime number theorem, well, it was conjectured a long time ago, but it was proved by a few people. So this was proved in 1896. I don't know, by Hadamard and de la Vallée-Poussin. Making sure that I write this. Poussin means chicks. So anyways, but so they use analytic approach for this. So the Riemann zeta function. Which is defined by a complex function. Zeta of s is the sum from n equals 1 to infinity of 1 over n to the s. It's not very clear, the connection to prime numbers when you write it like that, but the connection comes from the Euler product, which is the product of overall prime. Whenever I say p, it's all of primes, so 1 over p to the s inverse. So that's the connection to primes. And studying properties of the Riemann zeta function, they were able to prove the prime number theorem. So I'm not going to talk about that. I am teaching analytic number theory, where the goal is to actually prove the prime number theorem using this. But I'm not talking about that today. So nothing rigorous today. Okay. So we know that if you pick a big number n, n over log n of them is prime, roughly. But where are they? Are they a lot more concentrated earlier or later? And that's the question. So, so there is a generalization of the prime number theorem. So let's do that. So PNT for arithmetic progression. So sometimes this is called the Dirichlet's theorem or something. So let me just explain this. So, for example, you know that there are no primes of the form, I don't know, maybe 8n, because 8n is divisible by 8 and no prime is divisible by 8 by definition. But one could ask, are they primes of the form 6n plus 5, for example? that can contain primes, but then you want to count how many of them there are, primes of the form 6n plus 5. So you want to ask the question how many of them there are less or equal to a number capital N. So, well, that's a natural question. So so let's define, so for Q a natural number, that would be the 6 here, and an integer, that would be the 5. We could do the same thing. So define the function PQA of n to be the number of primes, or maybe I forgot about that earlier. Okay, I didn't forget. Okay, so the number of primes congruent to A mod Q such that that prime is less or equal to n. So the question is, how many primes are they congruent to 6n plus 5, for example, if Q is 6 and A is 5? And that's the theorem. So this is actually a theorem, a generalization of the prime number theorem, is that you get this is asymptotically equal to n over log n, so as usual, but then there's a constant in front, 1 over phi q. Okay, so of course right now you're probably thinking, why 1 over phi q? I'll explain that in a moment, but let me just define for people who forgot about phi. So phi, it doesn't depend on A, by the way. So phi q is the Euler torsion function, which is the number of A between 1 and Q, such that the GCD between Q and A is 1, so they're co-prime. All right. Okay, so that's a nice theorem, and but it's pretty much similar to the prime number theorem. So this was proved using, well, at least a modern proof, using, instead of a Riemann zeta function, you use something called a Dirichlet series. So a generalization of a Riemann zeta function. So something like this. There's a function on top, chi n, and I'm not talking in details about this. All right, where this thing is called so chi is called the Dirichlet's character. I'm missing an L. Mod Q if you started with Q there. But I'm not going to give you details about this. I'm teaching, as I'm saying, I'm teaching analytic number theory for honors, and I talk about this in details. Today, it's about understanding these theorems. For example, understanding why 1 over phi over Q and all of that stuff. So that's about primes. So let's talk about randomness then. Well, so the thing about primes is, if you study primes, then what does it mean to study primes? You're trying to find if there is, if you can guess something about primes. Like, for example, you want to see certain patterns in primes. So you try to find patterns in primes, for example, and then if you fail, so that means you cannot say anything about primes, then maybe there's nothing to say about primes. That means that primes are just behaving like any numbers similar to primes, if you like. So that's the idea of randomness. So primes are not random, but that maybe they just behave like typical set of numbers, like random sets, and that's what I'm trying to say. So the only thing that means that the only thing that we can find in primes, if primes behave like most sets, are the patterns that we would see in a set that we generate at random. So this is what is used a lot in analytic number theory. So that's most of the time analytic number theorists use heuristics to before they think about proofs. So it's that heuristics that I am going to talk about today. Okay, so how do we use that? Okay, so let's use a heuristic argument. So let's talk about first example. So example number 1. I'm going to talk about a few examples. All right, it's prime related, so it's still number theory. So let's say, okay, so this is a very nice example. A number is square free. We say that a number is square free. I'm defining square free if it is not divisible by, if it's not divisible by any perfect square. Greater than 1. So that's a square free number. So if you write this number down in terms of product of powers of primes, for prime decomposition, it does not have a power. Each prime that appears does not have a power greater or equal to 2. So that's a square free. So what is a square free number? For example, 6, for example, is a square free because the divisors are 2 and 3, and you can't really divide it by any square. 9 is not a square free because it's divisible by, well, it's square, so that's not a square free. So the basic question is, the same question as before. Let's say SF, square free, n is the number of natural number square free such that n is smaller than n. So we want to know, is there anything we can say about this number asymptotically? Okay, so there's a theorem. So this is an actual theorem that says that square free numbers, n is asymptotically equal to 6 over pi square times n. So then the question is, when you're not used to this, where does the 6 over pi square come from? Well, there is a nice heuristic argument, not a proof, just a heuristic argument. Just try to understand this theorem. So the idea is like this, so a heuristic. So heuristic argument, so this is the randomness. So the idea is divisibility is an independent event. So what do I say by that? Okay, so let's say let's R be a random number, uniformly at random, from 1 to n, right? So you pick a random number uniformly at random from the set 1 to n. And let's say we take 2 numbers, let's call them P and Q, such that the GCD between P and Q is 1. Okay. So what is the probability that R is divisible by P? So what's the probability that R is a multiple of P? Well, you just have to count how many multiples of P are there in this number and then divide it by n. What you'll get is, well, that's 1 over P, isn't it? Because it's about n over P, the multiple of P in there. So if you divide by N, you get 1 over P. And same, the probability of Q, R, that random number divisible by Q is also going to be 1 over Q. So let's calculate the probability that P divides R and Q divides R. So the intersection of the above events. Well, if P and Q are co-prime and P divides R and Q divides R, that means that the product of them, so P times Q, must divide R, right? Well, then it's just finding the number of number in here 1 to n that is divisible by P over Q, and that's roughly 1 over P Q. Oh, but that's exactly, well, I mean, let's use roughly because you miss a little bit in the end, but so that's almost the same as the probability that R is divisible by P times the probability that Q is divisible by R is divisible by Q. So if you have done any probability theory, that is independent. So that's independence of events. So divisibility by P and Q, if they are co-prime, it's independent. So so if the probability of the intersection is exactly the same as the product of the probabilities, then you get independence. Okay, so divisibility is independence then. So why does this have anything to do with counting prime squares? So that's, what am I talking about? Not square free. So let's say, what is then the probability that R is square free? So R square free. Well, if you want R to be square free, you don't want R to be divisible by, say 4 does not divide R because that's a square, so that's 2 squared. You don't want, you don't want 9, 3 squared, to divide R, and you don't want, what is next one, 5 squared, 25, to divide R, and so on. But since these are all co-primes, 4 is co-prime with 9 and so on, and these are almost independent, so that's the heuristic argument. They're co-primes using independence or almost independence because it's not exactly equal, it's asymptotic. This can be broken up into pieces, so 4 does not divide R times, using independence, 9 does not divide R, and so on. So what is that? Well, that is, it's a complement event. So it's 4 does not divide R. The complement of it is 4 divides R, and we know that probability. So the probability that 4 divides R is 1 over 4. So the complement is going to be 1 minus 1 over 4. The next one is 1 minus 1 over 9, and so on. All right. Oh, but that is equal to the product of all primes of 1 minus 1 over P squared. Ha! That's exactly 1 over zeta 2. So if you look at zeta 2, using the Euler product, it has a minus here with S equals 2, but you don't have that minus, so it's 1 over. But zeta 2, it's pi squared over 6, so that's why you get 6 over pi squared. So that's a heuristic argument. So that's why you get 6 over pi squared. But of course, if you have to prove this isn't a proof. It's just trying to make sense of the theorem. Of course, this proof can be, this heuristic can be changed to an actual proof by measuring exactly the independence, and you could argue this way. All right. So that's the first nice example. So let's do a second example. What color did I use? Green. All right. So let's talk about the prime number theorem in arithmetic progression. So thus. So we don't know why there is a phi 1/phi there, because we copy. So paste here. Okay, what about thus? Can we make sense of this without going into the proof of it? So does the 1/phi q make sense? Well, here's the idea. You're trying to count the number of primes of the form qn plus a. Okay, so what I'm going to do is I'm going to fix q and I'm going to let a vary. So I'm going to consider the set qa is equal to the set of qn plus a such that n is in z. This is an arithmetic progression, so it's a linear equation, so that gives an arithmetic progression. So there are a few things to talk about here. So first is that there are only q of these sets. Even though you are allowed to move a, there are infinitely many choices of a. Some of those choices will give you the same set. So the first set is going to be aq0. So those are the multiple of q. The second set is going to be aq1. The second set is going to be aq2, whatever q is. But the last one is going to be aq q minus 1. Of course, you're going to say, what about AQQ? Well, AQQ is exactly the same as this. So you know that the only thing that matters is the remainder of A when you divide it by Q. So that's why. So there's only Q of these sets out there, and those Q, those sets partition a Z. So the union of these sets, these Q sets, they are pairwise disjoint, and if you take the union, you get the whole set of integers. So that's good. So that's the second observation. Third observation is that if Q, because remember our problem is to try to find the prime numbers in this set. So if Q and A has a GCD D that is greater than 1, that means that all the elements of the set will be divisible by D, right? Because it must be divisible by the GCD of Q and A. And so if that's the case, then the set AQA can only contain I think it's just one, at most one prime. If D is a prime, but that's the only, so there can only be finitely many primes in such a set, and I think it's just one, because if D turns out to be a prime, then it is. But if D is not a prime, you can safely say that AQA does not contain any prime. So you have to delete all of this. So the only thing that, so that means that only AQ, only AQA such that Q and A are co-prime, so only the such thus can contain infinitely many primes. Okay, so only this that contain infinite. So among the Q, you're gonna have to those among the Q sets over here. You're going to have to remove those that has a GCD. Well, the GCD of this is assumed to be Q, so that's out. And those A, such that Q and A has a GCD greater than 1, those can only contain finitely many primes, so there are very little primes in them. So the remainder of the primes will have to go to these sets. So AQA, such that QA are coprime. Those are the only ones that can contain infinitely many primes. So if you want to count the primes from primes between 1 and n is assuming to be very large always. And the majority of these primes, like almost all of them, because only very few of them will be trapped in the above set. So almost all of them is going to be distributed among these guys, AQA, such that Q and A are coprime. And so, and how does it distribute? Does it discriminate against these? Well, any of these sets? The answer is no, because the assumption is that, well, prime is behaving like a random, so there is kind of a fair distribution among this. So that's the reason why that if you count prime and arithmetic progression, you get all primes. So that's all of them between 1 and n. And the reason why you have 1 over phi q, because only, well, how many a's are there such that q and a are coprime? Exactly phi q. So exactly phi q of this set can contain infinitely many primes. So what the primes do, they just distribute it among those guys equally, so that this is a fair distribution. So if you have phi q sets, okay, so let me write that here, phi q such set. So the primes just distribute fairly among this, and that's why you have this fair distribution. All right. So now this number here makes a lot more sense, because they're exactly phi q arithmetic progression of the form Qn plus A that can contain infinitely many primes, and apparently the primes just did not discriminate against any of them. It just distributes fairly. So that's why you have 1 over phi q for each one of them. So that's example number 2. So let's do, anyways, if you have a question, you can always interrupt me anytime. So just speak, and then I'll hear that there is someone talking. All right, 33. Okay, so I've got something like 12 minutes. Okay, I'm going to talk quickly about the twin prime conjectures, example 2. Example 3. So twin primes. It's a conjecture. So okay. So so let's say what is a twin prime, for example. So so a twin prime well, there's probably a lot of ways to define this, but a twin prime is a pair of the form p plus 2, such that p and p plus 2 are primes. Okay, so the conjecture is that the conjecture is that there are infinitely many of them. Okay. All right. Rocco, can you give me an indication that you are still there?
Yes, I'm still here.
Okay, good. I was feeling a bit lonely, so I was just yeah, but thanks. Okay, so there are many. It's a long-standing conjecture. Yeah, nobody knows what happens, but there is a much stronger conjecture than this. So let's just try to understand, if we want to count twin primes, what do we expect? So now that we know that, well, not that we know, but if we assume that primes are, behaving like most random sets, how many twin primes are there? So a naive heuristic argument goes like this. A naive argument goes like this. So what you do is, well, first of all, oh, by the way, let's just define something. Let's just define the thing that we like to define. Let's call pi to n be the number of prime less or equal to n, such that p plus 2 is also prime. So we're trying to count twin primes. Smaller, is that the first term is smaller or equal to n. So we're trying to count it. So the twin prime conjecture then claims that this function tends to infinity. Okay. Okay, so let's use randomness argument to kind of estimate how many twin primes should there be. So what you do is, well, so naive argument is you take a pair, so n plus 2, such that n is less or equal to capital N. And what you do then is you want to count how many of those gives you a pair of primes. Okay. Okay. So if you pick a random number, so if R is random in 1 to n, uniformly at random, what is the probability of picking a prime? So the probability of R prime, because of the prime number theorem, it's about 1 over log n, because it's the number of primes divided by n. So n over log n divided by log n. So that's that. So now, what we want then is, if you want to count twin primes, then you want R to be prime, and R plus 2 to be prime. If we assume that, independence, which we don't know yet, but if we assume that it's independent, so that if R, well, it's not independent, but then that's why I call this naive. But if R is a prime and R plus 2 is a prime, and let's say assume independence, then it's going to give you 1 over log n times 1 over log n. So 1 over log n for R to be a prime, and 1 over log n for R plus 2 to be a prime. So 1 over log n squared. So that would imply that the pi 2 should be about n times this probability. So it's going to be n over log n squared. So that would be the guess, and that tends to infinity because log is much slower than n. And we're not quite far off. So the actual conjecture is, we're not quite far off. In fact, the asymptotic formula is right there. So the actual conjecture is that this is some constant. Well, I'm not sure if there's a 2 in front, but there's some constant 2 of n over log n squared. So the main term, we got it. But the constant is the one that we need to think about. And this constant is the twin prime constant. There's a definition for it, but I'm not going to write it down, but it's about C2. If you look at twin prime conjecture, this will show up 6.6 ... This is a conjecture. And the reason why you have C2 is you have to do the following. Well, we can't really just take any pairs, because we know that if n is even, there is no chance that you're going to have a twin prime, because both are going to be even. And also, if you don't want any of the pair of numbers to fall into a multiple of a given prime, so you remove those obvious divisibility, then you correct this argument, and what you get is this correcting constant in front here. Nonetheless, that's still a conjecture. Nobody knows if it's true, but at least this conjecture is obtained from the assumption that primes just behave like a random set if we remove the the obvious arithmetic constraints, and that's where the sieve argument started. All right, so that was the twin prime conjecture. So you kind of understand, just very simple argument, you know why the formula are like this. So last, I'm going to give the last example. And this is, what is this? Example 4. Okay, so this is the prime number theorem itself, error term in PNT. All right, so okay, so what we want is so what we want is that if the set of prime numbers do behave like a random set, let's see how typical sets looks like, the number of elements of typical sets looks like. So what do I mean by that? Well, so let's just do this. So let's say I'm constructing a typical set. So T is a random set. And what I want is that I want it to have about the same density as the prime. So such that a number is in this set with probability 1 over log n, because I want it to have a similar density like the prime number, and I want to talk about this set. So I'm constructing a random set. So for each integer, that integer is in x. Well, so n is fixed here. So for each integer, that integer is in x with probability 1 over log n. Okay. So what is the number of elements in x? Well, the number of elements, it's a random variable, and it can be written as the sum from 1 to n of the indicator function, where n is in x. So if n is in x, then it's a 1 and so on. So the number of elements in there, because we're interested in the prime counting function. So x is just any set with the same density as the prime number, the prime numbers. So because this is a random variable, what is the expected value of the size of a random set? Well, that's obvious. It's exactly the sum from n equals 1 to n of the probability that n is in x, and because it's uniform, we said that n is in x has probability 1 over log n, and so this is going to be 1 over log n sum over n, you get log n. Okay, as expected, because it should have about the same number of elements as the prime, so it's about n over log n. But the question is, what if? So that's the main term. So the expected value is the main term. Oops, I was trying to talk about the error. What about the error? So what that correction term, if you do probability theory, the expectation is going to give you roughly the first guess, but the error term, how do we get that? And if you have done any probability theory, what gives the error term is the standard deviation or the square root of a variance. And by the way, this follows something called the binomial distribution, which is n over the probability, and you can calculate the variance. You can find the formula for that, and this variance, square root of a variance, is the standard deviation, and that's your error roughly. that would give you, if you look it up, the binomial distribution, I get what? The probability P, 1 over log n, times n. It's P times n times 1 minus B, but that's small. So square root, and so it's exactly equal to square root of n times log n to the power minus a half. Okay. Rocco, can I have 3 minutes?
Yes.
Okay.
Please continue.
Because okay, I'll have about 3 minutes. So if you have done any stats or probability theory, then you could say that most sets that falls in this category, well, because these are random sets, so they are, it's a represents so many sets, but most of them has size, the expected value, so there's enough concentration there. You could use central limit theorem or Chebyshev, I think, is enough to prove this. But n over log n, and the error is bigger of n square root, and then some powers of log. So some power of log. If you use Chebyshev, then you need a little bit more than this power to kind of make sense of the argument, but I'm not going to go into details. That's why we need some powers of log. But nonetheless, you know that a polynomial is much bigger than log, so this is much smaller. So if primes do behave like most sets, we should also have similar counting functions. So we should also have the prime counting function should also behave like this. But if it's really is just like most sets of its kind, then you should also have the same type of thing. Bigger of n to the half. Oops, I don't know why I wrote 3. Of some powers of log. You should also have this. And this is a conjecture. And which one is this? Does anyone know? Okay, it's the Riemann hypothesis. Because the Riemann hypothesis is definitely written a little bit more or differently. In fact, the Riemann hypothesis is about the zero of the zeta function. So the zero of this. So what is the statement of the Riemann hypothesis? If zeta of S is 0 and real part of S is positive, then the real part of that 0 is exactly half, and that's the Riemann hypothesis. And complex analytic number theory, so analytic number theory, so using the techniques of analytic number theory, you can link this half to this half. So if, say, the Riemann zeta function has a 0 at 3/4, for example, real part is 3/4, then this would become a 3/4. And so there's a link here, and this is purely complex analysis. I mean, it's a lot more advanced than that, but this is complex analysis, the study of zeta function. So that's the link. And so I want to end here because, and I wanted to give you the idea that the Riemann hypothesis is actually a randomness, well, you can view it as a randomness conjecture, because for a prime to behave like most set, what you see here is a half, and that's the half that comes in the Riemann hypothesis. And Riemann has a 2n, I think. So I stop here. Thank you very much for your attention and your patience.